Hello and welcome back to the channel. So today we will be discussing the third practice problem of this series on DP. This question is pretty simple, but it requires two-dimensional DP. So it will be a great practice problem for visualizing DP in more than one dimension. So let's get started and let's go through the problem statement first. It states that there's a robo on an m into n grid. The robo is initially located at the top left corner, that is grid 0, 0. The robo tries to move to the bottom right corner, that is the last cell of the grid. Now, the robo can only move either down or right at any point in time. Given the two integers m and n, return the number of possible unique paths that the robo can take to reach the bottom right corner. And also the test cases are generated so that the answer will be less than or equal to 2 into 10 raised to the power 9. So everything can be adjusted in the integer limit. Now to understand this problem better, let's go through an example. So at every step, we have two options, either to move down or right. So the robo starts from the first cell of the grid, and from the first cell, it has two options. It can either move towards right, that is to this cell, or it can move downwards, that is to this cell. Now, from these cells, again, the robo has two options. When the robo is at this particular cell, it can either move down or it can move towards right. So these are the two possibilities. And when the robo moved down, so again, it has two possibilities. Either it can take another step towards down or it can move towards right. Again, from all these cells, there will be two possibilities. So from this particular cell, there will be only one possibility. It can only move towards right because there is no option to move down. From this particular cell, there are two possibilities to move down or to move towards right. And also from this cell, it can move down or it can move towards right. So due to the two options at every step, there are multiple unique paths which the robo can take to reach the last cell. Now this clearly looks like a recursion tree because at every step we have two options and each problem is branching out into multiple sub-problems. Now let's just look at the first cell and try to apply a recursion intuition. If somehow we had the answer of what are the total number of different unique paths which we can take from this particular cell to reach the end, and what are the total number of unique paths we can take from this particular cell to reach the end. If we had these two answers, let's say that the answer from here was A and the answer from here was B. If we knew these two values, we could have easily calculated the total number of unique paths from this cell, which would have simply been A plus B. So the only unknown is the answers for these sub-problems which we can get from recursion. Because as recursion says, it will return the correct answer for sub-problems, just use them to calculate the current answer for the current cell. So this problem can easily be solved using recursion. Also, we need to think about the base case. So let's check the last row and last column. So every cell in the last column has only one option. We can only move down from here. There's no option to move towards right. So from here, we can only move down. From here, we can only move down. So from every cell in the last column, we just have one possible way to reach the end. Similarly, from every cell in the last row, we can only move towards right. There's no option to move down. So for every cell in the last row, we have only one way to reach the end. So the last row and the last column are going to be our base cases because we know that for every cell in this row and column, there's only one possible way or one unique way. Also, just to mention, the recursion tree for the problem will be a directed acyclic graph. The reason being that we only move right and down, so we can never take a turn and reach a combination of already visited row and column. So every step will explore either a new row or a new column. So we will not have any loops, and a sub problem cannot depend on a parent problem. So that's why we can apply recursion here. So let's quickly go through the recursive solution. So as we discussed, our base case is pretty simple. So base case is when we have reached the last column or the last row. So both in the last column as well as in the last row, there's only one unique path of reaching the last cell. So from there, we directly return one. We do not need to calculate anything. But for all the other cells, we have two options. We can either take a step down, so we can move to the next row, or we can take a step towards right and move to the next column. And we are delegating these duties to our recursive method because we know that our recursive method is going to return the correct answer for the sub problems. We don't have to worry about how. And just using those answers, we have added those answers and we have calculated the answer for our current step. and then we are returning that answer finally from here. So that is how, using recursion, we are calculating the answer. Now obviously this recursive method is not the optimal solution, and we get a time limit exceeded error. So again, let's try to draw a recursion tree and try to figure out that why is that happening. So let's draw a recursion tree for a 3 into 3 grid. So the grid will look something like this. There will be 3 columns and 3 rows. And let's give a name to each cell so that it will be easier to make the recursion tree. So it will be A, B, C, D, E, F, G, H, I. So we start from A and we have to reach I. So our recursion tree will look something like this. We will start from A. From there we can either move to D or we can move to B. From D again we can either move to E or we can move to G. Now G is a base case, so we won't expand the tree from there. From E, we have two options. We can either move to H or we can move to F. Now again, both F and H are base cases, so we won't expand the tree here. From B, we have two options. We can either move to E or we can move to C. C is again a base case, so we won't expand the tree there. And again, F and H. So as you can see that we have a problem of overlapping subproblems here as well. So we are solving the problem for E cell twice. Now the thing is that this grid was a little smaller, but if this grid would have been big, there would have been a lot of overlapping subproblems. But in this case, we just have one. We are calculating the answer for E again and again. And also we can see easily that this recursive tree is a directed acyclic graph. So definitely we can use dynamic programming to optimize a recursive solution, and our first choice would be to use memoization to optimize it. So let's see how does the memoization code look like. Now, as always, our memoization code is pretty simple and pretty close to the recursive code. So the only addition is that we also save the answer for the subproblem that we have already calculated. So if we have calculated the answer for a particular cell, so cells are represented by a pair of indices I comma j, which represent the row and column of the cell. So if we have calculated the answer for a particular I comma j, we store the answer and we do not calculate it again. So for storing that, we have declared a map in which the key will be I comma j and the value will be the total number of unique paths from that particular cell. The base case is same as the recursion. We have added an additional step in which we are checking if we have already solved the problem for a particular cell. So if we have already solved the problem, the answer would be existing in the map. So we are checking if there's an answer for I comma j in the map. If that is the case, then we'll simply return the answer. We'll not expand the tree again. But otherwise, we will solve and get the answer for that cell recursively. And before returning the answer, we will also make sure that we make an entry in the map so that we don't have to solve this problem again. Now let's quickly try to write the recurrence relation for this. So let's say that we have function f which returns the total number of unique paths from a particular cell I comma j till the end. So f of I comma j will be equal to 1 if I is equal to m minus 1, or j is equal to n minus 1, and otherwise f of I comma j will be equal to f of I plus 1 comma j plus f of I comma j plus 1. So this is the recurrence relation for our particular problem. Now we can easily model this as a 2D matrix where each cell is going to store the total number of ways from that cell to the bottom right cell. Now we can also build up our answer bottom up. If we start calculating the answer bottom to top and right to left. So if we have a matrix and we start calculating our answer bottom to top and right to left. If we are calculating our answer in this particular direction, now since a cell only depends on the cell which are below it or on the right, so all the dependencies for a particular cell would have been already calculated since we are following this particular order of filling up our matrix. And since all the dependencies for a particular cell would have already been calculated, we can easily calculate the answer for our current cell. So let's go through the tabulation code for this problem. So as discussed, we will first define a helper matrix m into n, which is going to store the answers for our DP. Now we will also fill up the base cases. So we know that all the cells in the last column and the last row have only one way of reaching the lastmost cell. So we are filling all the base cases using a for loop. So for all the cells in the last column, we are hard coding a value of 1, and for all the cells in the last row, we are hard coding a value of 1 again. So since the value for each cell only depends on the cell which are below it and towards right, when we are using this particular order of filling our matrix, all the dependencies would have already been calculated. So we are calculating right to left and bottom to top, and then we are filling up our matrix. So the value in a particular cell depends on the value for the cell below it and for the cell towards it, right? So we have already calculated this value, the total number of ways from the cell below it and total number of ways for the cell on the right, and adding those two values, we are getting the total number of ways from this cell to the bottommost and rightmost cell. And once we are done with these two loops, we would have filled the matrix, we would have calculated the total number of ways from each cell, and in the end we return the answer or the total number of ways from the first cell of the grid. Now talking about the time complexity and space complexity. So the time complexity and space complexity for this solution is big O of m into n, because we are creating a helper matrix of size m into n and we are parsing it and filling it once. So both space complexity and time complexity are m into n. In memoization also, we are calculating the answer for each cell once, just we are doing it top down. Since we are calculating the answer for each cell once and there are total m into n cells, so the total time complexity for memoization solution is also big O of m into n. So I hope that this problem and solution is now clear. In case you still have some doubts, feel free to initiate a discussion in the comment section, and I'll try to answer all the queries there itself. So I'll see you in the next video. Till then, take care. Bye bye.